For example, gas in liquids, like foams, or liquid in liquid suspension, like emulsions, or solid in liquid. So there's so many examples, fluidized bed and everything. Let's say cornstarch suspension or oobleck. And so in all of these colloidal systems, the elements of dispersed phase interact via hydrodynamic, thermal, and surface forces to give a colloid, which its rheology can be expressed by non-Newtonian rheology, like shear thinning, shear thickening, Yellow stress fluid, or viscoelastic fluids. And usually colloids are very complex. A colloid can exhibit several non-Newtonian features at the same time. For example, suspensions of cornstarch in water can exhibit Yellow stress, shear thinning, and shear thickening, depending on the shear rate that you apply on that. But the complexity doesn't end here. In fact, in many natural and industrial settings, we are dealing with dense suspensions that are systems of particles suspended in viscous liquid, and the particles size vary in a very long range. For example, in mud that we find in mudslide, landslide, submarine avalanches, or in biomass feedstock that we use to convert biomass into fuels, or the concrete that is the cement, paste, and aggregates. So in all of these examples, the fine colloidal particles interact to form a non-Newtonian matter, which itself drags along larger non-Brownian or non-colloidal particles. So we are dealing with a complex systems of particles suspended in a non-Newtonian matter, here after non-Newtonian slurries. And to give you a series of applications here based on what kind of suspending fluid we are dealing with. For example, when the suspending fluid is a Yellow stress fluid, the application is in mine tailings and converting biomass into fuel, fracturing or handling and disposal of waste, and natural disasters, mudslide, landslides, submarine avalanches. When we are dealing with shear thickening suspending fluid, the applications can be found in chemical mechanical polishing and semiconductors, and design of smart materials, shock absorbers like body armor fabrics, concrete industries. When it comes to elastoviscoplastic suspending fluids, the applications are more biological oriented, like drug delivery, blood cell segregation, and biolocomotion, and also oil recovery. So that has the importance and significance of this problem basically has set the theme of my research, and we are looking at microstructure, rheology, and fluid dynamics of these non-Newtonian slurries. But today what I want to do, I want to walk you through establishing a continuum framework for these non-Newtonian slurries and or suspensions of non-Brownian particles in generalized Newtonian fluids. And we know that when it comes to experiment, computation theory, we always have limitation. So the approaches that I'm going to adopt here are kind of hybrid, computation and experiment and theory, which I perhaps will not have time to explain, but a combination, a blend of everything I will be using to establish this continuum framework. And of course, it's very abstract. I'm not going to cover everything, but I suggest clever questions that you can ask me. So here we go. So I want to start with a brief review on the rheology of non-Brownian particles in Newtonian suspending fluids. And so here, imagine that you have an assembly of particles suspended in a Newtonian suspending fluid in a simple viscometric shear flow that you apply shear stress. Because of the existence of particle, you get normal stresses. This is in fact very different from that you get in viscoelastic fluid, okay? It comes from the presence of particles here. And in a Stokesian regime, if you want to come up with a closure for the stress in the suspension as a bulk, meaning that both suspending fluid and the particles, so the only scale that you have is viscous scaling, right? So this, the suspension stress can be the pressure part from the fluid, and also normal stresses that are developed due to the presence of this particle phase. and also the shear stresses that you have. And because you're adding particles into the suspending fluid, you're increasing the dissipation in your system. So you have to consider a multiplier for the viscosity that are so-called relative shear and normal viscosities that are increasing functions of the solid volume fraction. So there are empirical and theoretical relations for that. As you add particles in your system, the relative viscosity increases, and at some point close to the maximum packing fraction of solid, you get this divergence. So I can talk in the language of granular media or frictional view, but I'd rather not, so that I can translate the whole presentation, but this is the simplest way that I could say, and I'm sure that people are familiar with the authors of several papers that I listed out here. So as we increase the shear rate, what's going to happen? So in this case, when you're in Stokesian regime, the main mechanism for transport of momentum is this viscous stresses or the laminar drag around the particle escape. As you increase the shear rate, what's going to happen? You're going to have contact, collision, and you're going to have turbulent drag at the particle escape, and that adds to the suspension momentum. So in that inertial regime, you can expect that there should be another term in the suspension stress that scales quadratically with the shear rate due to inertial effect. And I'm going to write it down in this form because I like to use the particle Reynolds number. Okay, and this is the particle the Reynolds number at the particle escape. So this is the framework that we know in the Newtonian suspension. And the question is that how this closure can be modified when we are dealing with suspensions of non-Brownian particles in generalized Newtonian fluid. So this is what I'm going to talk about. Imagine that you have this suspending fluid that its rheology can be expressed by generalized Newtonian laws. In case of shear thinning or shear thickening fluid, you can adopt power law model, that is viscosity of the suspending fluid, that is the stress in the suspending fluid is this consistency times shear rate to the power of n. N smaller than 1 is going to give you a shear thinning suspending fluid, meaning that viscosity drops as you increase the shear rate. And larger than 1 is going to give you a shear thickening fluid, meaning that viscosity increases by applied shear rate. If you have the yield stress, the simplest way is to adopt the Herschel-Barclay model, meaning that the total stress comes from yield stress and the viscous dissipation, okay? And alternatively, you can write these laws in terms of shear stress is apparent viscosity times shear rate, and because these laws are nonlinear, the apparent viscosity is not constant, unlike Newtonian fluid, and it depends on this shear rate, okay? So, and this is a graph that you can basically plot all of these laws with that, okay? So now, what I want to do, I want to add particles into this generalized Newtonian suspending fluid and ask this question. What is the bulk rheology of this suspension? Imagine in dense regime of particle, I can assume that everything is, the dynamics of particle is controlled by the geometrical constraint in the leading order. Therefore, I can adopt the same relative normal and shear viscosity as that of Newtonian fluid and write down the shear viscosity or the particle pressure or normal stresses or this apparent viscosity times that relative viscosity times shear rate. But then we know that this apparent viscosity is a function of the shear rate, which is not the case for the Newtonian suspending fluid. But what shear rate? As we add particles into a suspending fluid, particles see a local linear variation of the bulk velocity, which is different from the average shear rate over a larger neighborhood. And this is the viscosity that is seen by the particle. For Newtonian suspending fluid, it's constant, we don't care. But this is not the case for the generalized Newtonian fluid, and this apparent viscosity depends on this local shear rate seen by the particle. Now, if we assume that, again, this local shear rate is mainly imposed by the dynamics of particle, which itself to the leading order depends on the geometrical constraint or solid volume fraction, we can link this local shear rate to the average shear rate over a larger neighborhood via a geometric function that I'm going to call it hereafter f of phi. There are theories to calculate this function via perturbation close to the jamming or homogenization theory. But we've recently, in collaboration with Olivia Poulicon and Elizabeth Guzzelli, measured it experimentally. I'm going to talk about it shortly. So having all of these ingredients, I can substitute back and come up with a closure for the suspensions of non-Brownian particles in generalized Newtonian fluid. And this is, in summary, that's the message. You start with a power law suspending fluid. You add particles into that. The rheology is still power law, but with the consistency that depends on the solid volume fraction. You start with the Herschel-Berkeley fluid. You add particles into that. The rheology is still Herschel-Berkeley, but with yield stress and consistency that are functions of solid volume fraction. Okay, so this is I made so many assumptions here to come up with this closure. Let's test them. The way that we test them here, we're going to use a pressure-imposed rheometry that is basically an annulus that is rotating, and on the top we have a perforated plate that we push on the grain to measure the stresses that are developed in the particle phase, okay? And the plate is free to move, therefore the solid volume fraction adjusts itself to give me the normal stresses in the particle that is equal to the imposed pressure. So we impose pressure and shear rate, and we measure solid volume fraction and the shear stress. What we do first, we adopt a different yield stress suspending fluid. We add particles, polystyrene particles, density match is the system, and about 500 micron size in particles. We add into that and we do the test, okay? The very first thing that we have to check is the following. I adopted the same relative shear and normal viscosity as that of Newtonian fluid. If this is the case, the effective friction, that is the ratio of shear stress to particle pressure, should be the same for Newtonian fluid and generalized yield stress fluid. And we test that, and we see that this is the case. Basically, our data for independent of the suspending fluid, our data collapses on a master K. The other assumption that I made was that in dense regime, the local shear rate is just a function of the solid volume fraction. Again, when we measure this geometric function experimentally, we realize that this is in fact true in dense regime. And so we're good. So all of the assumptions are going to work in dense regime. And now we have all the ingredients to test what is the yield stress of the suspension and consistency of the suspension as we increase the solid volume fraction. Okay, so these are some scatter data from previous literature performing conventional rheometry, and you can ask me why they are scattered. But in the dense regime, if I want to be French, I would say thanks to this pressure-imposed rheometry, we get a consistent result. So, so the question is that does this scaling argument work for other suspending fluid, other type of suspending fluid? And the answer is yes, maybe. And I want to summarize all the literatures, including those that I performed recently, to show this is in fact true. So imagine that you have a shear tuning suspending fluid, you start adding particles in that. People have shown that the effective viscosity increases, that we know, but they also show that the onset of thinning basically shifts to a smaller shear rate. And the reason is that the time scale that sets this dynamic now is the local shear rate, okay? Is associated with the local shear rate, and as you add particles, the local shear rate increases in the system, and that's why. And I can adopt the same framework to overlap all these curves on a master curve. The same goes for the yield stress fluid that I talked about. people are so into this shear thickening suspending fluid mainly because there is still debate on the origin of shear thickening. You can ask me about that. And people shown that then they have continuous shear thickening, meaning that viscosity has a slight rise and continuous rise with shear rate. We add particles into that, the overall viscosity increases, and the onset of CST shifts to a smaller shear rate. Again, we can formulate it with this scaling law. And recently, we've shown that this is also the case for the discontinuous shear thickening when the suspending fluid shows an abrupt jump in the viscosity. Again, by adding particles, not only we increase the effective viscosity, but also we shift, we enhance this shear thickening, and we shift this critical shear rate to smaller shear rate, mainly because now the local shear rate plays the most important role. Okay? So a question that you can ask me is that it is too good to be very true. Can you give me some examples that it fails? And then, so if I go back to the general closure that I introduced, so in case of generalized Newtonian fluid, I can adopt the same closure. However, here, now the apparent viscosity and the particle Reynolds number depends on the viscosity that is defined by what particle C, the local shear rate, okay? And what I showed here was just measuring two components of normal stresses in the solid phase, and you can ask me how you're going to measure the other component, and I would be happy to answer, and ask me because I'm excited about that one. And now the question is that how I'm going to measure this inertial contribution to this closure. And for that, I am going to adopt a computational approach. This is the work in collaboration by a group of Luca Brandt and PhD work of D.I. Galibi. I am not going to explain the computational method because Luca already gave his talk. So basically the same IBM code we adopted. What we are doing here, we have these suspensions of particles in shear thinning Newtonian and shear thickening fluid, and we apply shear rate and we push it to large particle Reynolds number here in the range of 0 to 10, and for the solid volume fraction that varies from 0 to 40. And we want to see how it affects the effective shear viscosity or effective relative viscosity, if you wish. So here is the case. So for Newtonian shear thinning and shear thickening suspending fluid, when particle Reynolds number is almost 0, we have a good collapse of data on those empirical relationships for the Stokesian regime. However, as we increase the particle Reynolds number, we see that the effective viscosity increases and we deviate from this Stokesian prediction. And the answer is why. So his group already answered that for the case of Newtonian suspending fluid, and this is the following. So the viscosity increases as we increase Reynolds number in the plane of viscosity versus Reynolds number for different volume fraction. We can call it using some shear thickening in the suspension. The answer is the following. As we increase the particle Reynolds number, a wake region appears behind the particle that with the zero probability of finding another particle there. And that shadow region increases as you increase the particle Reynolds number, as if you have an excluded volume in the system. So it increases a solid volume fraction in the system, and if you take that into account, basically you can see that you can map all of the points back in the Stokesian regime. So what inertia does here, inertia affects the microstructure. And by affecting the microstructure, it changes the viscosity. But we wanted to formulate that into our closure and how we can do that. So recently we did this complete study of the stress budget. So we know that the stress in the suspension coming from the viscous part, Reynolds stresses, and the particle stresses. Particle stresses include the particle acceleration, short range interaction, lubrication, collision, contact, okay? And we will look at these different components to see what's happening really as I increase the inertia in the system. So for the case of viscous stresses, if I divide the viscous stresses in two successive simulations that I increase the shear rate, the scaling should be viscous, okay? And if I plot for Newtonian suspending fluid, shear tonic suspending fluid, and shear thickening suspending fluid, the stress ratio based on the basically viscous scaling for a constant solid volume fraction, they should all cluster or overlap on these lines to show the code is valid, which is true. Okay, so but what is unknown here is, okay, for all of these simulations, we are in the particle Reynolds number of 0 to 10, meaning that the bulk Reynolds number is below 1000. So I am in laminar regime, so Reynolds stresses are negligible. So, but how about the particle stress? That's the main contribution, and we don't know what is that. If we plot the ratio of particle stress and we adopt this scaling, viscous scaling, can say that, okay, for all of these suspending fluids, we have clusters of data around that, but how about if I plot that based on the quadratic scaling or the inertial scaling? All of the data fall below this line, meaning that what we do in the range of solid volume fraction and particle Reynolds number is the following. Increase inertia, solid volume fraction is not dense enough to do anything except than changing the microstructure. That change of microstructure increases the viscous dissipation, and that's what we are seeing. So initially I wanted to understand what is this term. But what I ended up understanding was that we need to refine our relative viscosities by including microstructure that are produced in the system due to inertia. Okay, so this is what we came up with. But then, how we are going to compute this term or measure this term? This is something that I would say would appear in larger solid volume fraction and in higher particle Reynolds number. Everyone in this room is expert in the computational field, and you know that as you want to push it to the jamming, it's getting very difficult. So that's one computational challenge that we are working right now, and that with the group of Luca Brad. Or we can design a model suspension to be able to measure that. And we did that in my lab. So if you come to APS, please come to the talk of my PhD student. I am so excited about that. This is another question that you can ask me. And we reveal a new mode of shear thickening by these experiments. Okay, I'm not going to explain that. But what I wanted to say is that the whole closure things and continuum establishment for this dense regime came to me when oil industries wanted to ask us this question when I was a postdoc in the group of Ian Frigard. What is the Taylor dispersion of solid particles in a generalized Newtonian fluid? So Taylor dispersion is that how if you add a pulse of solute in fluid, how it disperses. And Taylor showed that this is a basically diffusive problem, but the question was that what is it for when it's not solute, when it's not a passive scalar, but particles? You can ask me this. I am not going to answer that. So, but what I wanted to tell is going to go back to Raphael's talk, that she mentioned that the kinetic theory closures. When I wanted to solve that problem, the very first approach that I took was to go to Gidaspo book and look at all of these kinetic theory closures and come up with the stress closures and solve that dispersion problem. But then I backpacked and went to Europe, in France in particular, and worked with all of these fantastic people in the field of granular theory, and I realized all of my modelings were wrong. And I want to show you just this simple slide that goes back to your talk. If I adopt those closures that are coming from the kinetic theory, that are based on binary collision, that kind of does not include the contact, the friction into the system, this is what I get. So in this plot, you are looking at the dissipation of the fluctuation energy in the system. So this line is the closures that I showed and partially validated via experimental and computational results. So the red curve shows the inertial contribution, and the black curve shows the viscous contribution. You see that as we increase the particle Reynolds number, immediately passing particle Reynolds number around 1, the whole dissipation comes from the contact, collision, and friction. However, if you adopt the kinetic theory, this is how much you get. This is very different. And I think this system, I would be happy to sit down with you and show my mathematical algorithm, but I don't think it's gonna work. And if you want more detail, look at this paper by Ian Freegard that we did. So in summary, I walked you through establishing a continuum framework for suspensions of non-Brownian particles in generalized Newtonian fluid, and we included inertial effects, we included microstructure, and this, I didn't get a chance to talk about it, but we developed a mathematical framework to address the dispersion of solid in thin film flows like natural disasters, and hydraulic fracturing, or mainly geophysical flows. And I want to acknowledge the financial support of NSF, ERC, ACS, PRF, and ANR. And I want to, in particular, thank to NSERC, who gave me this opportunity through this postdoctoral fellowship, that I could backpack and go to Europe and work with fantastic people and understand this problem very well. And these are graduate students that I want to acknowledge, undergraduate students, and my collaborators, Luca Brand, Simon Daguaboy, Ian Freegard, Elizabeth Bizzali, Nicola Lenova, Bloen Mesker, Guillaume Wallace, and Olivier Poulican. Thank you for your attention. Yes?